Hello everyone, welcome you all to the live session 6 on the course of Fundamentals of Manufacturing Process. So here we will be looking at some sample problems which are based on the lectures of the week 6. So let's quickly get started. Yeah, this is the first problem. First of all, please try to solve it by yourself and try to give the answer in the chat box. After that we will discuss it together. If you have got the answer, then you can type it in the chat box. Yes, correct. So let's discuss it together. So in the problem 1, it is being asked about the draft in the rolling process. So I will quickly draw an schematic of the rolling process. Basically, aim of the rolling process is to reduce the cross-sectional area of the workpiece, or let's say billet. So this is the workpiece, or let's say or billet, and initially it was having shape something like this. But finally what we want yes, we want this is the final product. Yes, earlier we can see the cross-sectional area was something like this, and finally it has been reduced. It will be better if I would show the dimension. This is the length, this one is the width, and this one is the initial thickness. And after deformation we want new length, let's call is capital L. Here width will be the same of initial one, and thickness will be TF, which is basically we want to reduce the thickness and as well as the cross sectional area. Here one thing we have to note it down, that width of the billet is not changing even after the rolling. So from here to here, how can we go? We can go with the process of the rolling. We will try to pass this billet in between two rollers. Basically they will be rotating in such a way so that billet would pass in between them, and there is a gap. This is called the roll gap. We give the roll gap in such a way so that the final thickness will be equals to this roll gap. So what we do, we try to apply the force when this roller keeps on rotating and this billet enters in between them. Then these both rollers put the compression force on the billet, and because of this force this billet cross sectional area get changed or material gets deformed. So overall in this process what we did, we had initial thickness of T0 and finally we are getting the TF final thickness, and initial length was small l, capital length is capital L. On width we have kept the same. So this can be achieved with the help of process of the rolling, and this difference basically T0 is greater than TF, we can see in the picture, and this difference of thickness is known as the draft. So draft is defined by the difference of initial and final thickness. So correct answer for this question will be the third one. So I think it's clear to all of you, and if any of you have any doubt you can ask me, otherwise we shall move to the next question. Okay, it seems there is no doubt, so let's move to the next problem. Please read the question and try to solve it by yourself first, and you can give your response in the chat. After that we will together discuss this question. And if you feel any difficulty in understanding the question, you can ask me. So in this question, apart from roller diameter, assume everything is constant, then probably you can find the answer. Yeah, I'm waiting for responses. It looked like there is some difficulty in understanding the question, so let's solve it together. So in this question it has been given that the radius of the roller is increased in the case of a rolling process, then draft would be, as we have discussed in the previous question. Yes, as we have discussed in the previous question, that draft is defined by draft basically it is a difference of thickness of billet before and after the rolling. So what will happen if we increase the roller radius, or let's say a roller diameter? Then we will try to see with the help of the schematic. Suppose we have two conditions of the rolling. Here we have a roller with having a small diameter, and let's try to make another schematic. Yeah, Hardik, you are correct. Okay, so basically here we are trying to compare the effect of the roller diameter on the draft. So first I have drawn two rollers with having a roll gap of, let's say, TF, and now we will draw another set of rollers with big diameter. And here also we will keep the roll gap same. So here roll gap is same in both cases, which is TF. With small diameter, small radius, rollers with large radius. And if you can remember, there was a parameter, basically it is called bite or angle of bite, and which is defined as basically if we are having the billet and the point of contact, where basically the angle between the point of contact to the point of exit, so that angle is called the angle of bite. And as I told, you have to assume all other things constant except the roller diameter. So here for both cases we are considering the angle of bite is theta. here also angle of bite will be theta. So in both cases we can see, in the case of a smaller roller, the for fixed angle of bite and for fixed final thickness we are having, let's say we are giving a name here TF1, and here we are giving the TF2. Sorry, not, it should be T0. TO1, T02, and here TF is the final. Now let's try to calculate the draft for these two cases. So for first case where the we have smaller rollers, here we will calculate the draft. It will be equals to T01 minus TF, and here if we calculate the draft, minus TF. So if we see from the diagram, then it's clear that the T02 is greater than T01. Why it has happened? It has happened only because of, in case of larger diameter for same angle of bite, we can feed the larger thickness of billet, whereas if we have smaller rollers, then for same final reduction and for same angle of bite we can feed only we have to feed smaller thickness of the workpiece, and because of that we are getting this difference. So let's call it D1 and let's call it D2. Since T01 is smaller than T02 and TF is the same for the both case, therefore this condition implies that the D2 is greater than D1. It means D1 was the initial draft and D2 is the newer draft. So what happened? Draft value has been increased. So correct answer for this question will be increase. If we increase the radius of the roller, then draft value will be increase. So I think I have explained the solution of this question. If still any of you have any confusion, please unmute yourself. Okay, it looks like it's clear to everyone, so we will move to the next question. Please read the question and try to get the answer. Meanwhile I will create the polls, and now you have to give your response in the polling section. Yes, I have launched the polls. Please keep your response there. After that we will discuss it together. I have got a few responses. I am still waiting for others. Okay, two of you have got the correct answers. So let's discuss it for the everyone. If you can you think of uh, where the crankshaft are used? If you can think of, then can you type it in the chat? You can type where you can think of some examples where crankshaft is used. Yes, Hardik, correct. You are correct. Yes, yes. Crankshaft are very common in the IC engines, and this is how it look like. Basically, in IC engine, we know we have pistons, and those pistons are attached with the shaft, and that shaft is called the crankshaft. Basically, uh, sorry. Yes. So uh, these pistons are inside the cylinder blocks, and uh, when fuel burns, then because of the uh, it there is generation of the pressure when the fuel burns inside the cylinder, and because of that force gets generated, and that force comes on the piston, and this piston is connected. This is the piston, and this is the connecting rod, and this connecting rod connected to this shaft, and this is called the crankshaft. So when fuel ignites inside, let's say this is the cylinder, when fuel burns inside cylinder, then huge amount of force is generated, and that force transferred to the connecting rod, and with the help of connecting rod, that force gets converted into the torque uh, for the crankshaft, and because of which we achieve rotary motion inside the IC engines. So if we see its geometry, just if you look at the shaft, it's very complex in the nature. So it's not mostly, if we say about the shaft, then normally what happens, it's a cylindrical in shape, and if it has some slot for the key, that's all. Normal shaft is have very simple geometry, but crankshaft has very complex geometry, basically because of these counterweights. And this type of uh, complex geometry cannot be made by the processes like such as like rolling, or even for the extrusion. So the best way to produce this kind of geometry are, if we talk about metal forming process, forging is the process from which we can manufacture this kind of complex geometry, and this kind of complex geometry can also be made by casting process, which we have studied earlier in the course. And it is also possible to manufacture the complex geometry with the help of machining process, but that will be very costly. So if we look at the question, the process which are listed here is the rolling process, machining process, forging process, forming process. So uh, since this geometry is very complex, and we cannot we cannot manufacture it by with the help of a rolling process. So that is ruled out. So in whatever we want to produce this kind of component with the help of rolling, it will be very kind of very difficult, or let's say impossible, to achieve this much of complexity through the rolling process. So machining process, I told that it is possible, but that would not be a best approach, and it will be a very costly and time consuming if we produce a crankshaft with the help of machining process. But we have to look for the best process. So that is also not correct answer for the problem. And I told that the forging process, let's look at the forging process. If you can remember from the lecture, in forging process, uh, what we do, we have initially we have let's say we call it billet, and slowly, by providing the compressive force on this billet, and mostly at the higher temperatures, we try to do shape change of the billet step by step manner. If you could remember, there were several processes like fullering, edging, bending, blocking, finishing, trimming. So all steps are done, and finally we do trimming, and we can get this kind of geometry. And this kind of forging we can do with the help of die. Basically, we have several sets of die, and in first process, what we will do, we will have die, and we put the billet there, and we apply the compressive force. And we keep temperature little high, so that its yield strength will become smaller, and metal have ability to flow. High temperature, so basically it's the hot working process. And first set of die we forged it, and then we got this, but this is not the final shape. It is somewhat somewhat near to the very initial shape of the this crankshaft. And after that we use another set of die, and we again try to forge it similarly in this manner. After 4 5 uh, after 4 5 sets of die, we will able to get our final product, which is a very complex geometry, and all final product is achieved by the applying compressive forces in the forging process. So this is very energy efficient and time efficient process, as well as, so here we are doing hot working, and in forging we are applying compressive force. So properties like strength, toughness, and it's a hardness, all these properties get enhanced in this process. So therefore this process is good in two ways. One, we can easily achieve the complex geometry, and another is we will get very good mechanical properties. Because when when crankshaft basically uh, when it stays inside the engine, and when large amount of force get transferred to the shaft, so these properties help to sustain the shaft. And also here fatigue properties. Since here cyclic loading is happening, therefore fatigue properties also required, and all these properties can be achieved with the forging process, and with very less amounts of cost and very less amount of time. Therefore this process is the best process to manufacture the best quality of the crankshaft. And fourth option is the forming process. So forming process is not itself a process, it is just a lot many process comes under the forming process, uh, like a rolling, extrusion, and forging, and there are many more. So basically forging is the just part of the metal forming process, and therefore the forging will be the correct answer for this question. So if any of you have doubt, please unmute yourself, you can ask me, or we shall move to the next question. Okay, it looks like it's clear to everyone, so let's quickly move to the next question. Please read the question and try to solve it, and meanwhile I will create the polls. You can give your response in the polling section. After that we will discuss it together. I have launched the polls. Please try to find the answer, and you can give your response in the polling section. I have received a couple of responses. I'm still waiting for others. Okay. Yeah, most of you have got the correct answer. So let's quickly discuss it for others. It is being asked that the frictional forces in between the billet extrusion die is relatively high in the case of. So here are the options listed down, like forward extrusion, backward extrusion, hydrostatic extrusion. Same in all cases. Let's quickly look on each process, and then we will decide that which one having the highest frictional forces. So this is the schematic of the forward extrusion. So here basically this is the billet, and there is a dummy block. This is a dummy block, and this is the plunger, or let's say ram, and we are applying force on the plunger, and this plunger is pushing the dummy block, and this dummy block is pushing the billet. And basically what is happening here, by when this force is applied on this billet, then it because of compressive forces it tries to deform, and it tries to deform with the help of die, and basically the material will experience reaction forces from all sides, and wherever it finds the space it tries to flow through that direction. Basically whatever the material is there, because of compressive forces it will tries to flow towards the opening of the die. Likewise this material in all regions tries to flow towards the die opening, and finally the billet takes the shape of the opening of this die part. And now let's try to look at what are the where are the regions, what are the regions where frictional forces are acting. We know frictional forces act on the surfaces where there is a relative motion is being taken place. So that kind of surfaces are like here in this region. Okay, I should choose some other color. Yes, these are all the regions where I have hatched in green colors. All these regions are uh, the surface contact with relative motion. Basically this billet portion is also moving forward, as well as material inside the billet is moving towards the die opening. So friction between this wall and this billet, this wall and this billet and this wall will be present, as well as the friction between die portion will also remain present during the extrusion process. So this is the all friction region which we have hashed down in the forward extrusion process. Now let's look at the backward extrusion process. Here what is happening, here we are having billet in this region. So this is the region of the billet, and now this is the die. This is the die, and this die is being pushed with the help of this hollow plunger, and we are applying force towards billet, and in between die we have given the opening, and because of again compressive forces, when we apply compressive force on the billet, so again material will try to flow in those direction wherever it will get chance to escape. So like here material from all sides starts moving towards the die opening and finally coming out of the die and taking the shape of cross section of the die. Now let's start look at the what are the contact surfaces where a relative motion is being between the billet and the die part is taking place. If you see, billet is stationary. Billet is stationary in this container region. Only movement of material is taking place between these regions. So these are the only regions where the contact relative motion is taking place between the billet and the die, whereas the other portions like these portions they are in the contact of the die container but they are not moving, so frictional force will not be active in those regions. So only frictional force will act in this region and in this region, whereas earlier it was a very large region of frictional forces. So at least if we compare forward and backward extrusion, we can say in forward extrusion the frictional forces are high because of they have a larger contact area of relative motion between billet and the die. Now let's see the third option, hydrostatic extrusion. So in hydrostatic extrusion it's very similar to the forward extrusion, but here what we do, we are using fluid. Basically we are using fluid. Why we are using fluid? Basically we are trying to apply a force on, not directly on the billet, we are applying force on the fluid, and fluid has a very good property. When it experiences a force or let's say pressure, then it has very good property that wherever it remains in the contact with the any other surface, it applies equal pressure to all the contact surfaces. So whatever pressure will be here, let's say here pressure is P, then here also, everywhere the pressure which is acting on each surface of contact of between fluid and the die, or let's say fluid and the billet, everywhere the pressure will be P. And because of this condition is called hydrostatic extrusion, where a body experiences equal pressure in all directions. So that condition is known as the hydrostatic conditions. So in all directions the billet is experiencing equal amount of pressure. This basically helps in reducing the cracking tendency of the billet. Suppose if we have any material which is brittle in the nature, then if we apply the force only in one direction, suppose if fluid was not there, we would have applied force directly on the billet, then there was possibility of getting generation of the crack, because we have applied the force only in the one direction. Then in other direction there is a possibility of crack propagation, but now fluid is there, so force pressure has been applied on the billet in the all directions. So in all directions crack propagation is reduced, and only way to come out of only way for the material is to flow in the direction of the die. So this is used for the brittle materials. And we know the friction between fluid and the die. This is the reason of the friction between billet and the die. Basically, friction forces between fluid and the billet is very small in comparison of the friction between billet and die. So here very small region of high friction is there, that is the near the die. Whereas these regions where the fluid is coming in the contact of the billet, these are having very negligible frictional force, almost zero. Therefore, if you compare the backward extrusion with the hydrostatic extrusion, here friction value will be lesser. Frictional forces will be lesser in the case of the hydrostatic extrusion, and if you compare the backward extrusion with forward extrusion, then frictional forces are higher in the case of forward extrusion. Therefore, the maximum friction force which will be acting in the extrusion process will be in the case of the forward extrusion. So forward extrusion is the correct answer, whereas the fourth option is same in all cases. It is wrong. So maximum will be in the forward extrusion and least will be in the hydrostatic extrusion. So if it is clear to everyone, then we can move to the next question, or I will wait for if any of you have doubt. Okay, it's clear to everyone, so let's quickly move to the next problem. Please try to solve it by yourself. Meanwhile, I will create the poll. You can give your responses there, and after that we will discuss it together. Yes, I have launched the poll. You can give your response in the polling section. I have got few responses. I am waiting for others. Okay, yeah, few of you have got the correct answer. So let's try to discuss it together. So collapsible tube. This kind of tube, I think you must have seen in your day-to-day life. Uh, so these are the collapsible tube, and mostly if you have seen the ointment tubes, they are made up of they are in this shape, and they are made up of metal, and they are collapsible, because when we apply some force, then they will get deformed, and we will reduce the volume inside the tube, and because of that, the whatever things, cream or ointment, what will be there, it will come out. So these are the collapsible tube, and how they are manufactured. So if you have gone through the lecture, then there was a process called impact extrusion. So this is the process from which this kind of tubes are made. The biggest the major thing about this tube is that the wall thickness is very small, very small wall thickness. So if we try if it is less than 1 millimeter, the wall thickness is less than 1 millimeter, so that kind of thin sections cannot be made by all the extrusion processes, and the best process to achieve this kind of thin sections of the wall is the impact extrusion process. So what we do in the impact extrusion, basically initially we have billet, or let's say slug. So both are the same thing, slug or billet. So that is kept in between the die. This is the die which have the shape similar to the tube, and in this die we keep the slug, and there is a punch, and we apply a impact force on this punch, and there is a very small gap between the punch and this die, and when we apply impact load on this punch, it will come down, and it will try to squeeze the material. So it will come here, it will try to material to deform. Then what will happen when it applies the compressive force on this material? Then material will flow in those direction wherever it will find the gap. So it will keep on coming down, and material will starts flowing from there to there, because this is the gap where this is the gap from where it is getting passed to flow, and this gap is very small. This gap is having similar thickness of this collapsible tube. So when we apply impact load, because of this impact load, a very small amount of time, the slug get deformed, and material flows very quickly in between the thin sections of thin gap between the die and the punch. So this is the process how we can achieve these very small sections or thin sections. Whereas if you try to make this kind of thin walls using the forward extrusion, or let's say backward extrusion, then again we have it is not possible to get that small thin sections in those cases. So that's why impact extrusion process, where we apply the force, which large force, which will in very less amount of time. Basically it is impact force, and because of this impact loading, metal quickly flows in the thin sections, thin gap, and finally we will able to manufacture this collapsible tube. So correct extrusion, correct answer will be the impact extrusion. For other processes, it is very difficult to get this thin sections. If we have larger thickness of walls, larger wall thickness or larger sections, then we could have used any of this process. But since the wall thickness is very less, only option is to go for the impact extrusion. There are another ways also to manufacture this kind of tubes that will come to later in this course, that is from the deep drawing. But till now what we have studied, out of that, impact extrusion is the process through which we can able to produce thin collapsible tube, thin walled collapsible tube. So correct answer is impact extrusion. If any of you have doubt, please unmute yourself, and if it's clear to everyone, then we shall move to the next problem. Okay, let's move to the next problem. Please read the question. It is related to the wire drawing process, and please try to give your response in the polling section. Meanwhile, I will create the poll. After that, we will discuss it together. I have launched the polls. You can give your response in the polling section. Okay, I have a few responses. One of you have got the correct answer. Let's try to discuss it together. So let's try to see the schematic diagram of the wire drawing process. Yes, this is the schematic of the wire drawing process. So this is the die region. These are all the die region. We have upper die and bottom die. Basically, it is not like upper and bottom. It's in 3D. So it's a just sectional view. So if we see in the sectional view, then it will look like that we have upper die and bottom die. In between, the material is being passed, or let's say we have bar. The purpose of wire drawing is to manufacture wire from the bars. Basically we have bar initially, and finally we try to reduce its diameter to, let's say, smaller one, and it is wire. So from bar to wire, we want to manufacture wire, and the process which is used to get the wire from the bar is called the wire drawing process. And what happens in the wire drawing process, we have die which is already there, and it has separate zones. So first zone, where the first the bar enters inside the die, the first it encounters with the entry zone, which is here. After that it passes through the approach zone, and finally it comes out through the exit, and this zone is called the relief zone or clearance zone, and in between there is a bearing surface. So this bearing surface have the final dimension of the wire. So how this is done? Suppose if we try to take a cylindrical bar and we directly try to put it into the die, will it it will able to pass through the die? No, it will not able to pass through the die. Suppose this is the bar and we are directly try to feed it. We are directly try to feed it with in the die without doing anything. We just took the bar and we try to feed it inside the die, and what we are doing, we'll try to pull this bar towards away from towards outside of the die, and we are expecting this bar will get deformed and it will take the shape of the die. If we don't do anything and we directly put the bar inside the die, then it will get stuck at the entry zone itself. So because it will not able to align in between the die, and it will hit the die, it will get stuck into the die. Therefore we cannot directly use this bar. What we have to do, we have to take the bar, and from the end where we want to start the wire drawing process, we reduce the cross sectional area to somewhat smaller diameter, and this process is called the swaging. This is done so that it could fit into the wire drawing die easily. Now if we try to insert this bar in this die, it will easily get into the die and it will not stuck anywhere, and it will not hit the die, and we can easily pull it from the end of this pointed end. Now we will pull it, and since it has come inside the die, basically it has been accommodated in the initial part of the die in very good manner. Now if we try to pull it, then we can easily go for the wire drawing process, and material will flow very uniformly, and we will able to get the wire. So zone, if you look at the question, zone which facilitates the entry of the pointed bar in the wire drawing process. So whenever the bar will come, the first region which will encounter with the bar, that should have capability to facilitate the entry of the bar. So first zone is entry zone. This zone, this entry zone, if our bar will pass easily from the entry zone, it will not get stuck here or it will not hit the die, then we can, other things are easy to do. So the first, if we easily able to pass through the entry zone, then we can easily go for the wire drawing. So the correct answer for this question will be the entry zone. So if any of you have doubt, you can ask me, or we can move to the next question. Okay, so entry zone is the correct answer, and I uh, I don't think any of you have doubt in this question. So let's move to the next question. Please read the question and try to think, and you can give your response in the polling section. After that we will discuss it together. Yes, polls are live. You can give your response in the polling section. Yeah, I have got few responses and I am waiting for others. If you have any confusion in the question, you can ask me. Okay, let's try to solve this question together. Two of you have got the correct answer. So let's quickly look at the process again. So how this wire drawing is done? So initially we have a bar, and we have a die, something like that, and we try to put the bar in the die, and now what we do, we try to pull this bar at very high speed through the die, and what happens, the bar takes the shape of the die, or its cross sectional area gets reduced, or the diameter of wire gets reduced as per the final die thickness, final die gap. So sorry, So what we are doing, we are applying a force F, but we know what is happening. Initially we has bar of higher diameter, finally we are getting a wire of less diameter. Will it be possible to reduce the diameter with the help of tensile force? Can we reduce the cross sectional, can we reduce this diameter just by putting the tensile force? If we pull it there, then also probably we can get then probably also we can reduce the cross section area, but it will not be a very uniform in diameter. Therefore we need a die, so that our surface finish is good and the cross sectional area is very uniform. So when we pull this bar, we apply force F. Indirectly what is happening, these are the regions where the bar is coming in the contact of the die. When we try to apply a pulling force on the bar, then die is providing reaction force on the bar, and this reaction force on the bar is compressive in the nature, and because of this compressive force, material cross-sectional area gets reduced, or its diameter gets reduced. The final deformation is of final deformation of uh, reduction in diameter is happening because of the compressive force which has been applied by the die. It is the reaction force which is being provided by the die, but that force is coming because of the pulling force which we are providing on the bar. So directly we are providing pulling force, and because of the reaction of the die, the reaction stresses are being the compressive stresses are being generated throughout the cross section of the billet, and because of these compressive forces, this reduction in diameter or area is happening. So locally if we see, the final deformation is happening because of the compressive forces with the help of die, but we are not providing any load in the die section. We are not applying any force on the die. What we are doing, we are just applying a pulling force on the bar, and because of reaction forces, the reduction in area is happening. So from user's end, we are applying a pulling force or tensile force, and therefore stress applied during the process of wire drawing. So we are applying tensile force, but indirectly this tensile force getting converted into the deformation force which is compressive in nature, and that is being applied with the help of the geometry of the die. So the correct answer for this question will be tensile. We are applying tensile force and compressive forces are being generated indirectly. So therefore correct answer will be tensile stress. So it is clear to everyone. If any of you have doubt, you can unmute yourself, or we shall move to the last question of the session. Okay, it seems there is no doubt. Let's move to the last question of the day. Please read the question and try to solve it by yourself. Meanwhile, I will create the poll. You can give your response in the polling section. After that, we will discuss it together. I have launched the polls. You can give your response in the polling section. Yeah, I have got a few of responses. Still, I am waiting for others. Okay, most of you have got the correct answer. Let's discuss it for everyone. Let's discuss it together. So, the question is the essential metal property which is desired for wire drawing process. So, what we do in the wire drawing process, as we have discussed in the earlier question, initially we had some bar, and from bar we try to make or manufacture a wire of thin cross-sectional area. And how we do it? We do it by applying a pulling force and passing the bar through a die. So from bar to the wire. So if we try to look at the options, we have toughness, ductility, yield strength, hardness. So all are the properties. Basically, these are the mechanical properties, and these are related to the material. So directly, indirectly, all of them are important, but one property which is the most which is the which are which is mandatory, which is the most important property which is needed for the wire drawing. So that property is the ability of material to get elongated. So if material have ability to get elongated, then only it can be, this bar can be converted into the wire, and that property is called ductility. And how it is defined? So ductility is defined by percentage elongation. Let's say percentage elongation, and which is given by L0 minus LF upon L0 into 100. So suppose initially we have bar of dimension L0, and finally its dimension gets converted into its length changed to the LF, and then by using this formula we can say this is the percentage of elongation, and that is called the ductility. So this is the very essential property which material has to have in order to get it drawn into the wire. So whereas if we talk about the other properties, let's say strength. So strength is the, so basically strength is the minimum value of the stress which is applying on the material. After that, plastic deformation starts happening. So if we look at the stress strain diagram, then what happens, how the metallic materials behave. So they have typically this kind of behavior. So we try to apply the force on the material, then it will uh, deform elastically means it will recover its shape after removing the load. So this is the reason. So this is the elastic deformation reason. And after that, this is the reason of plastic deformation. And from and the point from which this elastic deformation changes to the plastic deformation, that is called the yield strength. So if uh, if this is yield strength of the material will be very high, then again we have this wire drawing process will be difficult. We have to apply large amount of force to deform the bar into the this wire shape. So that is the yield strength we want, it should be the low. And if we talk about the hardness, yes, hardness is also related to the strength only. If material have higher strength, then it will resist the plastic deformation. So if material will resist the plastic deformation, then it cannot be permanently deformed. Basically, it will be difficult to deform permanently, or it will be difficult to convert this bar from convert the bar into the wire. So desirable property will be the low hardness, low strength, and toughness. So toughness is what? Toughness is the energy absorbed, total energy absorbed during plastic deformation before fracture. Here it should be total. So basically, when we try to deform the material, it requires energy. When we deform the material plastically, then mechanical energy, uh, because of this mechanical energy, the shape of material gets changed. And from the user point of view, we definitely want a process which should consume very less energy. It should not require large amount of energy. Therefore, we want a material with lower toughness. So in order to convert this bar into the wire, we want a material which should have lower toughness, higher ductility, lower yield strength, lower hardness. So the essential property which is desired, it should be the ductility. We need it higher. If it will be higher, then we can easily convert this bar into the wire. So correct answer will be the material should be a ductile. So I think I have explained the question. Still, if any of you have any doubt, please feel free to ask me. It is clear to everyone? If it is clear to everyone, then uh, we will end the session here, and we will meet in the next week at the same timing. In our okay, Hardik has doubted in our fundamentals of manufacturing course which type of yeah, question will be simple only. So basically, whatever is being asked, what are the concepts, numerical or the theoretical things which is being tasked, which is being taught in the question. From that only you will get the questions in the final examination. Uh, there it may be you have to write the answers in your paper, and you have to upload it. Basically, answer can be descriptive type. Also, it may be possible the questions can be objective types, numerical types. So that will be only from the lectures only. So the format will be anything like numerical type, theoretical type, descriptive type. So it can be anything, but it will be totally from the course content which has been delivered to you in the whole course. So that will be easy only. So if you have gone through the all lectures, if you have done all the assignments by yourself, then you won't face any difficulty to get the good marks in the examination. So I think I have answered the Hardik, it is clear. Yeah, don't worry for the exam. Just you go through the course material and try to solve all the assignment by yourself. You will definitely score very well in the exam. You will get very good grades. So any of you have any doubt? Yeah, if no doubts are there, then we can end this session here. So wish you all very happy weekend. Till then, go and enjoy, and next week we will meet with similar kind of question based on the lectures of week 7. Till then, thank you. Bye bye.